Alright, let us continue with part 2 of this topic on convection, fundamental concepts of convection. Okay, so we have any surface of arbitrary shape or a flat plate. Whenever the surface temperature Ts is different from the temperature of the flowing fluid next to it, we have definitely heat transfer to or from the surface. So far, we have looked at the boundary condition where the surface temperature is stated clearly, different from the flowing fluid. Let it be known that actually there are 3 types of boundary condition in convection heat transfer analysis. One of which we have considered earlier, often considered, that is isothermal constant temperature on the solid wall. What you have been introduced to, call it the Dirichlet boundary condition. The temperature is explicitly given on the wall. The second boundary condition, or the second condition for heat transfer in convective mode of heat transfer, is the given constant heat flux on the solid wall. Earlier we mentioned about the Newman boundary condition. Yes. And the third boundary condition is what we call unheated starting length on the wall. In this course, we shall look at only the type 1, type 2 conditions for convective heat transfer. Yes. For case 1, the surface is assumed at a uniform temperature Ts, and as mentioned earlier, if Ts is not equal to the fluid temperature, convection heat transfer will occur. So now what we are interested in is the total heat transfer due to convection from or to the surface. Now we have the total heat transfer, heat flux multiplied by the area, because it varies over the surface with Newton's law of cooling. You get this equation. Now we define an average convection coefficient H bar for the entire surface where convection occurs as this. Note the bar on the edge. That is the average heat transfer coefficient. Now H without the bar is the local heat transfer coefficient, which varies along the distance x from the leading edge. For a flat plate, one-dimensional, H varies with x from the leading edge. So you can hear the leading edge. This is taken from Chengel, figure 7.9. You see in the laminar region, the heat transfer coefficient decreases with x, and then during the transition, which for external flow is about Reynolds number 5 times 10 to the power 5. Yes, and it increases within the transition region, and then it drops again in the turbulent region. Yeah. So for the average heat transfer coefficient, we have this equation for constant plate width where convection occurs. You can see here how you take the derivative of the area, surface area, from here. Okay. Note that in the Chengel book, the average heat transfer coefficient is not written as H bar. So please read the text carefully when selecting the most appropriate H correlation for your heat transfer rate or heat transfer. Yes, as given in 6.1 and 6.2. So if you have noticed here, the local flux or the total heat transfer rate are of paramount importance in any convection problem, which depends on the local H and the average H. Yeah? Thus, it is viewed that the determination of this coefficient is the problem of convection. So compare that with your conduction mode of heat transfer. When you're interested to determine the temperature profile or the heat loss heat gain, K is the value you need to determine dependent on temperature, and boundary condition here is all about H in convection. Yeah? So convective heat transfer H depends on fluid properties. density, viscosity, thermal conductivity, specific heats. Note that these are thermophysical properties. Yeah, so they are temperature dependent. That means they change with temperature. So it's very important at which temperature you take the values in your calculations. Then there is the surface geometry, smooth or rough. You know, rough surface tends to initiate turbulence earlier during the flow. And flow conditions, laminar or turbulent, which depends also on the velocity of the flow of the fluid, among other things. So let's have a look at the property tables in the textbook. Now please take time to look at the data that you have in the appendices. Yes, don't take those for granted. Look at the patterns and trends as the temperature changes. In general, note that, yeah, for liquids, yeah, as the temperature increases, the viscosity decreases. For gases, as the temperature increases, the viscosity increases as well. You can look at other properties. Some may change significantly with temperature, while others do not. Let's look at the laminar and turbulent flow. Yes. So surface friction and the convection heat transfer rate depends strongly on the flow conditions. You can see from the diagram that we have here a transition region before the laminar flow fully become turbulent. And in the turbulent boundary layer, this is a boundary layer, remember earlier in part 1, even in the turbulent boundary layer, you can actually subdivide it into 3 sub-layers. Yeah, laminar sub-layer, buffer layer, and turbulent region. That's all I'm going to say about the sub-layers within the turbulent boundary layer for information purposes. Yes. So there are sharp differences between laminar and turbulent flow, as you have learned in your fluid class. Yeah. So in many cases, both conditions may occur with the laminar section preceding the turbulent section. Here I've listed down some significant differences between laminar flow and turbulent flow. For laminar, fluid motion is orderly, so you can see clearly the streamlines. Meanwhile, in turbulent flow, the fluid motion is highly irregular in all directions. It's no longer one-dimensional, but multi-dimensional in turbulent layer. So in the laminar flow region, velocity components in x and y directions are clear, if there are any at all in the y directions, particle, yeah. But for the turbulent flow, they are chaotic. Yeah. So laminar boundary layer is thin, yes, thin, generally thin, and the turbulent boundary layer is thicker and more uniform. Yes. Conditions in the transition zone. Yes, this zone, this transition zone, yes, may change with time. The flow sometimes behave as laminar and other times as turbulent flow. Yeah. Experimental and analytical studies have suggested that streamwise vortices are generated intermittently near the surface. They grow and they decay, and other coherent structures within the turbulent flow can travel in waves at velocity that exceed the streamwise velocity, nu infinity. So I've mentioned about the sub-layers here. In most of our studies, however, we look at only the laminar and turbulent region. We ignore the transition region. So for external flow, we say that at a certain Reynolds number of about the magnitude 10 to the power 5, the flow becomes turbulent. When in actual fact, yeah, there is the region what we call transition region. We ignore that in this class. It's much easier, but it's not correct. Yeah. So the transition from laminar to turbulent is due to triggering mechanisms such as interaction of unsteady flow structures, rough surfaces, others. Reynolds number. Okay, you're all familiar with Reynolds number, right? Yeah. Okay, so the Reynolds number is actually the ratio of the inertial forces over the viscous forces. which one is more significant in a flow. If the viscous forces are more prominent, then we have very low Reynolds number. Now, if the initial forces are much larger, then we have the very large Reynolds number, okay, which in that case generate turbulence faster. Yeah. So it's a dimensionless parameter. Keep that in mind, and please notice the units involved. Yeah. So also for external flow, we refer to the characteristic length as the length of the distance that the fluid flow. For internal flow, this would have become the diameter, hydraulic diameter, yes, as well as flow over circular cylinders, which will come across much later. Yeah. So X is measured from the leading edge. You know what is the leading edge? Yeah. For large Reynolds number, the initial forces can amplify the triggering mechanism and the transition to turbulence occur. Now, we call the critical Reynolds number, where transition to turbulence occur, as that Reynolds number subscript XC. Yeah? The critical length where the transition to turbulence occur is this term. Yeah? So, for a flat plate, external flow, turbulence approximately is initiated at Reynolds number of about 10 to the power 5 to 3 times 10 to the power 6. Yes. So why do we bother about laminar and turbulence region? Because the heat transfer coefficient varies. Yes, you can see here that the heat transfer coefficient decreases in the laminar flow region, increases within the transition region, and decreases again within the turbulent region. So it's very important to determine that your area of study, of analysis for convection heat transfer, yeah, is in the laminar or turbulent region. Because like I said earlier, we tend to ignore the transition region. It's much more complex to analyze. Yeah? So determine early whether your flow is external or internal. And with this external, you have to determine the critical length where the flow starts to become turbulent. And that will determine which correlation to get your heat transfer coefficient. I mentioned much earlier when we started the part 1 of convective heat transfer lecture, you'll be introduced to two very important dimensionless numbers. You have known Reynolds, now you meet Prandtl number. Okay. Prandtl number is just the ratio of the molecular diffusivity of momentum. Yes, that is the mu multiplied by Cp and divided by molecular diffusivity of heat, which is just K. Simplified, you can get this 612 equation in your Cheng-El. Now, the Prandtl number ranges for fluids from less than 0.01 for liquid metal to up to above 100,000 for heavy oil. This is about 10 for water. For gases, Prandtl number is about 1, which means that both momentum and heat dissipates through the fluid at the same rate. Why? Look at this. If this is approximately 1, then the numerator and the denominator is about the same order of magnitude. Yeah. So if you look, if it is very, very large, let's say greater than 100,000, you have known that actually the diffusivity K is very, very small and mu Cp is large. Vice versa for liquid metal. The other important dimensionless number is the Nusselt number. Okay, so remember this very, very well in heat transfer. Prandtl number and Nusselt number. So the dimensionless number associated with heat transfer coefficient is defined as the Nusselt number here, convection over conduction. Yeah. So that means, yeah, for a significant convective heat transfer, you have a Nusselt number larger than 1, of course. Yeah, it represents the enhancement of heat transfer through a fluid layer as a result of convection relative to conduction across the same fluid layer. Okay, I'm going to stop that. So that is part 2 of our topic on fundamental concepts of